Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the Pump Operations Study Guide. This guide is designed to give you a comprehensive overview of essential pump knowledge for wastewater treatment operators. We'll cover topics such as centrifugal pumps, maintenance procedures, troubleshooting techniques, and operational best practices. So, over the next few slides, we'll walk through these key areas to help you become more confident and effective in your roles. Let's get started. Let's talk about bearing temperature and lubrication, which are critical factors for maintaining equipment health. First, there's the critical temperature threshold. When bearing temperatures go above 160 degrees Fahrenheit, it signals serious operational issues. This isn't something to ignore. It's an early warning sign that something might be wrong and needs immediate attention to prevent further damage. Next, overlubrication can actually cause problems. It might seem counterintuitive, but applying too much lubricant can lead to overheating and even bearing failure. The excess lubricant increases friction and heat, which reduces both the efficiency and lifespan of the bearing. So more isn't always better. Moving on to bearing failure indicators, high temperatures are often the first sign that a bearing is starting to fail. That's why regular temperature monitoring is so important. Catching these signs early helps us prevent catastrophic damage and costly repairs. Finally, under-lubrication is just as problematic. When there's not enough lubricant, friction increases, leading to more heat generation. Maintaining the right lubrication levels is essential for optimal bearing performance and to prevent premature wear. In the context of overall equipment reliability, keeping an eye on bearing temperature and lubrication levels helps us avoid unexpected failures and keeps our machinery running smoothly. Let's talk about shaft coupling and alignment, a major factor in equipment longevity. One of the primary causes of coupling wear is misalignment between the pump and motor flanges. When these components aren't properly aligned, it creates uneven stress distribution across the coupling. This uneven stress accelerates wear patterns and can significantly shorten the lifespan of your equipment. To prevent this, proper alignment during installation is crucial, and regular checks during maintenance are just as important. Now, there are a few key considerations to keep in mind. Angular misalignment, for example, causes uneven load distribution, which leads to increased stress on the coupling. Parallel offset, on the other hand, creates excessive radial forces that also contribute to wear. When misalignment is combined, both angular and parallel, it multiplies the wear rates exponentially. That's why consistent verification of alignment helps prevent costly repairs down the line. It's worth noting that while discharge pressure and seal condition do impact overall pump performance, they don't directly cause coupling wear. The mechanical connection between the pump and motor must stay precisely aligned to ensure efficient power transfer and reduce stress on components. Here's a pro tip. Use tools like dial indicators and laser alignment devices. These help you achieve the kind of precision alignment that manufacturers specify, typically within 0.002 inches. Staying on top of alignment is a simple yet effective way to extend your equipment's life and avoid unnecessary downtime. Let's take a closer look at the packing gland components, starting with the lantern ring. A lantern ring is essentially a spacer ring that we install in the pump packing gland. Its main function is to improve the distribution of seal water around the shaft. This metal component creates a chamber that allows the seal water to flow evenly, which is crucial for proper lubrication and cooling of the packing material. Now, why is this even distribution so important? Well, the lantern ring ensures that the seal water flows uniformly throughout the packing chamber. This even flow helps prevent hot spots, which can cause damage or rapid wear. It also reduces friction and helps extend the life of the packing by maintaining consistent lubrication across all the packing rings. Finally, the placement of the lantern ring is key. It is positioned between the packing rings and connects directly to the seal water supply line. Proper installation and placement are critical because they ensure effective seal water delivery. When everything is correctly positioned, It leads to optimal packing performance, especially in centrifugal pump applications. Overall, understanding these components and their functions helps us maintain efficient and reliable pump operations. Let's take a closer look at some of the common pump types you'll find in wastewater operations. First up, we have centrifugal pumps. These are by far the most common type used in wastewater applications. They operate by using rotating impellers to move liquids through inertia and mass, creating a circular motion. The key here is that they convert rotational kinetic energy into hydrodynamic energy, which makes them highly efficient for high-flow, low-viscosity fluids. They're also praised for their simplicity, reliability, and low-maintenance needs, making them a favorite choice in many treatment facilities. Next, we have diaphragm pumps. These are positive displacement pumps, meaning they move a fixed amount of fluid with each cycle. They use a flexible diaphragm that reciprocates, creating alternating suction and discharge strokes. This design makes them particularly well-suited for handling abrasive slurries, chemicals, or fluids with suspended solids. One of their big advantages is that they're self-priming and can run dry without damage, which adds to their versatility across different wastewater treatment scenarios. Finally, let's talk about submersible pumps. These are designed to operate while fully submerged in the liquid they're pumping. The motor and pump are sealed in waterproof housing, which means there's no need for priming, and they tend to generate less noise. You'll often find them used in wet wells and lift stations. They're space-efficient and protected from weather elements, but it's important to remember that maintenance and monitoring need to be planned carefully since they're submerged. All three types, centrifugal, diaphragm, and submersible, are frequently encountered in wastewater treatment plants. Each has its specific strengths and applications, depending on flow needs, fluid characteristics, and installation requirements, which helps us choose the right pump for each particular job in our overall treatment process. Let's take a closer look at how centrifugal pumps operate, focusing on their fundamental principle of inertia and circular motion. Essentially, these pumps work because of the mass moving in a circular path. When the impeller spins at high speeds, it transfers kinetic energy to the liquid, thanks to centrifugal force. Here's how it works in practice. The liquid enters the pump right at the impeller eye, which is the center of the impeller. As the impeller rotates, its vanes accelerate the liquid outward, pushing it from the center toward the periphery. This outward movement is driven by centrifugal force, which is the key to how these pumps move fluid efficiently. As the liquid moves outward, this kinetic energy is transformed into pressure energy within the volute, or the spiral casing surrounding the impeller. That pressure then pushes the liquid out through the discharge pipe, ready to be used in the system. What makes centrifugal pumps stand out compared to other types? Well, they are simple in design and highly efficient. Unlike airlift pumps that use compressed air, diaphragm pumps with reciprocating membranes, gear pumps with meshing gears, or piston pumps with reciprocating pistons, centrifugal pumps rely on this circular motion and inertia. This simplicity and efficiency are why they are the most common choice for wastewater applications and many other fluid transfer needs. They are reliable, easy to maintain, and capable of handling large volumes of fluid with minimal energy loss. Now, let's take a closer look at the bubbler control systems. First, we have the air pressure generation component. A small air compressor continuously supplies low-pressure air through a tube that extends into the wet well. This tube is positioned at a fixed depth below the liquid surface, ensuring consistent measurement. Next, the pressure sensing part comes into play. As the liquid level in the wet well changes, it affects the back pressure in the air tube. When the water level rises, it creates greater back pressure, and when it drops, the pressure decreases proportionally. This variation in pressure is then monitored by a pressure transducer or switch, which converts the pressure into an electrical signal. This signal accurately indicates the liquid depth in the wet well. Finally, this information feeds into the pump control system. Based on the pressure signal, the system can automatically start or stop pumps at specific levels. This helps maintain optimal operations, preventing both overflows and damage to the pumps from running dry. It's important to note that unlike flow meters, the bubbler system doesn't measure flow rate, and unlike aerators, it doesn't prevent septic conditions. This makes it a reliable, non-contact method of level sensing, especially in wastewater applications. It's unaffected by foam, turbulence, or floating debris, making it a preferred choice for consistent, accurate level detection. Now, let's take a closer look at how centrifugal pumps are classified based on flow direction. This is a fundamental aspect because it directly impacts the pump's performance and suitability for different applications. First, we have the radial flow pumps. In these, the liquid enters the impeller axially, that is, straight into the eye, and then exits radially at a 90-degree angle from the impeller. These are the most common type, especially for general wastewater pumping. They are known for delivering high head, which means they can generate a strong pressure rise at moderate flow rates. They're particularly effective for clean to moderately dirty liquids. Next, axial flow pumps. Here, the liquid flows parallel to the pump shaft, moving straight through the impeller, kind of like a propeller. These are ideal when you need a high flow rate, but at a low head. Think of large volume transfer or circulation systems. They're often used in applications where volume is more critical than pressure. Then we have mixed flow pumps. As the name suggests, they combine features of both radial and axial flow. The liquid exits at an angle somewhere between radial and axial, providing a balanced performance. These are suitable for medium flow and head applications, often found in wastewater treatment where versatility is key. It's important to remember that while the power source and liquid type are also important considerations when choosing a pump, the flow pattern defined by the impeller is what fundamentally determines the pump's hydraulic performance and operational envelope. Understanding these classifications helps us select the right pump for the right job, ensuring efficiency and reliability in our systems. Let's talk about proper packing gland leakage. Ideally, during normal pump operation, you should see about 1 drop of fluid per second leaking from the packing gland. Now, this might seem like a problem at first, but actually, it's a critical part of the design. That controlled leakage helps ensure the packing performs well and lasts longer. So why is this leakage necessary? First, it provides lubrication. The fluid that leaks out keeps the packing material and the shaft sleeve lubricated, reducing friction and heat buildup. Second, it helps cool the system. The escaping fluid carries away heat generated by the shaft's rotation. Third, it prevents the packing from drying out and hardening. Without enough moisture, the packing can seize on the shaft, causing damage. And finally, maintaining proper lubrication and cooling significantly extends the service life of both the packing and the shaft sleeve. Now, let's address common mistakes. Over-tightening the gland to eliminate all leakage might seem like a good idea, but it actually causes problems: overheating, rapid wear, shaft damage, and even bearing failure. On the other hand, zero leakage suggests the packing is too tight and will likely fail early. Conversely, too much leakage, more than 1 drop per second, wastes water and could mean the packing is worn out and needs replacing. When adjusting the packing gland, it's important to do this gradually and evenly while the pump is running. Stop tightening once you see that 1 drop per second. After installing new packing, give it about 30 minutes of operation before making the final adjustment. Remember, maintaining the right leakage rate is key to ensuring the longevity and efficiency of your pump system, aligning perfectly with our overall goal of reliable, long-lasting equipment operation. Let's talk about impeller wear and how it impacts energy consumption. When a new impeller is installed, it operates at its optimal efficiency, thanks to tight clearances between the impeller and the wear rings. This means it uses energy effectively for the rated flow and head, ensuring everything runs smoothly. However, over time, abrasive materials in wastewater gradually erode the impeller vanes. This wear increases the clearances, which in turn reduces the pump's efficiency and can change its performance characteristics. Essentially, the pump isn't working as effectively as it should. As the impeller wears down, it requires more energy to move the same amount of fluid. This is because larger clearances allow some of the liquid to recirculate internally. Basically, the fluid leaks from the discharge back to the suction side. This internal recirculation wastes power and doesn't contribute to productive work. The more the impeller wears, the harder the pump has to work to maintain the same discharge rate. This increased clearance means more liquid recirculates inside the pump, which causes the motor to draw more current. That results in higher energy consumption and ultimately higher operating costs. That's why regular inspection and timely replacement of wear rings are so important. Restoring the impeller's original clearances helps maintain efficiency and reduces unnecessary energy waste. Staying proactive with maintenance keeps the pump running smoothly and economically. When you notice that a centrifugal pump is discharging at a reduced rate, the first thing to do is focus on the hydraulic components of the pump rather than the electrical parts. Often, the issue stems from something obstructing or impairing the flow within the pump itself. One common cause is a clogged impeller. Debris, rags, or solids can accumulate on the impeller vanes, restricting the flow passages and reducing the pump's capacity, especially in wastewater applications. The good news is that inspection and cleaning usually restore normal flow quickly. Another typical issue is a worn impeller. When the impeller vanes experience abrasive wear or when the clearances at the wear rings increase, the pump becomes less efficient. It might still run, but it won't deliver the same flow rate. In such cases, replacing the impeller or the wear ring is necessary to bring performance back up. Air entrainment is also a common culprit. Air leaks in the suction piping or through packing glands can significantly reduce pump capacity. Additionally, vortexing in low wet well levels can introduce air. To fix this, check for proper submergence and seal all connections on the suction side to prevent air from entering. Discharge obstructions are another factor to consider. Partially closed valves, clogged check valves, or restrictions further downstream in the discharge piping increase the system head, which in turn reduces flow. Always verify that all valves are fully open and inspect for any blockages downstream. It's important to note what these issues are not. For example, a blown fuse would prevent the motor from running altogether, and higher than normal voltage would usually increase flow, not decrease it. So, when troubleshooting reduced discharge, your main focus should be on hydraulic issues, clogged or worn impellers, suction problems, or restrictions in the discharge piping. That's where the problem usually lies. Let's now compare mechanical seals and packing, and understand why mechanical seals are increasingly preferred in pump applications. Mechanical seals are favored mainly because they eliminate the undesirable leakage associated with packing. You see, packing requires a certain amount of leakage for lubrication and cooling, which can lead to water waste and environmental issues. Mechanical seals, on the other hand, provide a much better solution by preventing visible leakage altogether. Now, what are the advantages of mechanical seals? First, zero leakage. When properly maintained, they stop water from escaping, helping us save water and reduce environmental impact. Second, they require less maintenance because they don't need regular tightening like packing glands do. Third, they tend to last longer if maintained properly, operating for years without needing replacement. Energy efficiency is another big plus. Mechanical seals generate less friction than packing, which means they consume less power. Plus, they keep operations cleaner. No dripping means a safer, tidier work environment. And finally, they protect the shaft from wear caused by the friction of packing, extending the life of the shaft and related components. Now, let's look at packing limitations. Traditional packing needs a controlled leak, usually about 1 drop per second, to keep the packing lubricated and cooled. But this constant dripping wastes water, creates slip hazards, and isn't environmentally acceptable, especially in modern facilities. While packing may be cheaper up front, the ongoing water loss and maintenance costs make mechanical seals more economical over time. It's also important to note that mechanical seals are not more tolerant of shaft misalignment. In fact, they require very precise alignment. They are actually more sensitive to issues like misalignment, vibration, and shaft runout than packing. So, proper installation and maintenance are crucial for their effective operation. In summary, while both have their roles, the industry is clearly shifting towards mechanical seals because of their efficiency, environmental benefits, and long-term cost savings, though they do demand careful handling and precise alignment. Let's talk about the dangers of over-tightening packing glands. When you tighten the glands too much on a pump shaft, it can trigger several failure modes that seriously impact the pump's performance and lifespan. One of the first issues is that it causes overheated bearings and can even lead to bearing failure, which then accelerates shaft wear. This small mistake in maintenance can set off a chain reaction resulting in catastrophic pump failure. Now, what happens immediately when you over-tighten? Excessive gland pressure increases friction between the packing and the shaft sleeve. This friction generates heat right away, meaning the pump has to work harder and consume more power just to overcome that resistance. Plus, the packing itself begins to dry out and harden, which only worsens the problem. As the heat builds up, it's transmitted along the shaft to the bearings. This causes the bearing temperature to exceed normal operating limits, often going beyond 160 degrees Fahrenheit. When this happens, the lubricant inside the bearings starts to break down, losing its protective qualities and making the bearings even more vulnerable. This increased friction and heat also cause the shaft to wear out faster. The hardened packing acts like an abrasive, gouging grooves into the shaft sleeve. Over time, this results in a scored, rough shaft surface. This damage then speeds up the packing's wear, creating a destructive cycle that's hard to stop. If the overheating continues unchecked, it leads to bearing failure. The lubricant carbonizes and becomes ineffective, which causes the bearing components to suffer heat damage, excessive wear, or even seize up completely. When bearings fail, it often means costly emergency repairs and significant downtime for the pump. That's why proper packing adjustment is so critical. It's a delicate balance, tight enough to control leakage to about 1 drop per second, but not so tight that it hampers lubrication and cooling. It's essential for operators to resist the temptation to tighten excessively in an attempt to eliminate all leakage, because doing so can cause these serious problems we've discussed. Now, let's walk through the steps for restoring a pump after installing the packing and the last ring. Once you've completed the packing installation, it's essential to follow a complete startup procedure to ensure safe and effective operation. First, start with the initial gland adjustment. Take up the gland bolts finger tight only. This gives us initial compression without over-tightening, which is crucial. Then, make sure to tighten the gland bolts evenly. Uneven tightening can cause the gland to cock, leading to uneven pressure distribution and potential leaks. Next, we start the pump and let it run. Remember, new packing needs some time to seat and conform to the shaft sleeve. During this initial period, expect some leakage. This is normal as the packing adjusts to the operating conditions. While the pump is running, monitor and gradually tighten the gland bolts. The goal is to reduce leakage to a tolerable level, typically about 1 drop per second. Make small adjustments and always wait a moment between tightenings to observe how the packing responds. It's very important to verify that you tighten the gland bolts evenly throughout this process. Uneven tightening can cause high-pressure spots, which accelerate wear, or low-pressure areas, which can lead to excessive leakage. Once you've completed the initial adjustments, allow the pump to run for about 30 minutes to let the packing break in properly. After this break-in period, perform a final adjustment. During this time, check the packing temperature and leakage rate to make sure everything is within acceptable limits. A key point to remember: never tighten the packing glands with the pump stopped. Adjustments must always be made under operating conditions. This ensures the packing seals properly with adequate lubrication. Patience and gradual tightening are critical. They prevent over-tightening and help achieve the best packing performance. By following these steps carefully, we ensure the pump runs smoothly, efficiently, and with minimal wear over time. Let's take a closer look at the factors that determine pump capacity. The main elements are speed, impeller, and casing. These three components work together to define how well the pump performs and how much fluid it can move. First, regarding speed, or RPM, rotations per minute, this directly impacts capacity thanks to the affinity laws. When we double the speed, the flow rate also doubles. So, controlling the motor speed, drive ratios, or using variable frequency drives allows us to adjust capacity effectively. Next, the impeller design is crucial. The diameter, vane configuration, and width all influence how much liquid the pump can handle. Larger impellers and more aggressive vane angles tend to increase capacity. Conversely, trimming the impeller reduces capacity, which can be useful for fine-tuning performance. Then there's the casing configuration. The volute or diffuser casing converts velocity energy into pressure energy. Its design impacts efficiency and the relationship between flow and head. Larger casings are better suited for higher flow rates. Now, to understand how these factors interact, let's look at some key effects related to speed. When speed doubles, the flow doubles as well. However, the height the pump can lift, actually increases by the square of the speed ratio. Power consumption, on the other hand, increases by the cube of the speed ratio. So a small increase in speed can lead to a much larger increase in power demand. By understanding these interactions, we can better predict how a pump will perform, troubleshoot capacity issues, and select the right pump for specific applications. Manufacturers provide performance curves that show how capacity varies with both impeller size and speed for each casing size, helping us make informed decisions. Now, let's take a closer look at the dual purpose of the water seal. First, its primary function is lubrication. The seal water acts as a lubricant between the packing material and the rotating shaft sleeve. This is crucial because it helps to reduce friction, which in turn minimizes heat generation. Without this lubrication, both the packing and the shaft components could overheat and fail prematurely. So proper lubrication is essential for the longevity and reliability of the pump. Next, the secondary function of the seal water is to serve as a barrier. It keeps gritty materials, such as dirt, sand, and debris, from entering the packing box. The pressurized seal water flows outward through the packing, creating a hydraulic barrier. This barrier prevents abrasive particles from reaching the packing area, which significantly extends the life of both the packing and the shaft sleeve, especially important in wastewater applications where such contaminants are common. Typically, the seal water system connects to a clean water source and is delivered through the lantern ring in the packing gland. Maintaining proper seal water pressure, usually about 10 to 15 psi above the pump's suction pressure, is key to ensuring both effective lubrication and barrier protection. If the flow is too low, grit can infiltrate and cause wear. Conversely, if the flow is excessive, it wastes water without providing additional benefits. It's also important to clear up some common misconceptions. Seal water does not keep the pump primed. That's the job of the casing and suction line. It does not cool the bearings. That's handled by specialized bearing lubrication systems. And it's certainly not a reserve water supply. Its roles are strictly to provide lubrication and create a barrier to protect the packing in demanding environments. Understanding these functions helps us appreciate how critical proper seal water management is for pump performance and longevity. Let's talk about the maximum pump elevation above the supply source. The key point here is that we generally shouldn't place a pump more than 22 feet above the supply. This limit is rooted in fundamental atmospheric pressure principles and practical pumping considerations. Now you might wonder why 22 feet specifically. Well, at sea level, atmospheric pressure can support a water column of about 34 feet, given the standard 14.7 psi. But in real-world applications, the practical suction lift is limited to around 22 feet. This limitation comes from several factors. First, friction losses in the suction piping reduce the pressure available at the pump inlet. Second, the vapor pressure of water, especially in warm conditions, reduces the net positive suction head the pump can handle. Third, altitude effects decrease atmospheric pressure as you go higher above sea level, further limiting lift capacity. and temperature increases vapor pressure, which can lead to vaporization within the pump. All of these factors mean that exceeding this 22-foot limit increases the risk of cavitation, which can cause vibration, reduce pump efficiency, and even lead to damage. That's why most engineers recommend keeping suction lifts to 15 feet or less for reliable operation. When higher elevations are unavoidable, it's better to consider using submersible pumps or positioning the pump below the liquid source to ensure smooth operation and avoid these issues. Now, let's talk about check valves in centrifugal pump systems and why they are so essential for flow control. Check valves are used alongside pumps to prevent wastewater in the discharge line from flowing back into the wet well when the pump stops. This backflow prevention is critical because it ensures the system operates correctly and maintains efficiency. When the pump is running, the discharge pressure opens the check valve, allowing wastewater to flow smoothly through the discharge line to its destination. During this time, the valve remains fully open, facilitating continuous flow. Once the pump shuts down, the flow momentum doesn't stop instantly. Instead, it continues briefly due to inertia. As the flow begins to reverse, driven by gravity and system pressure, the check valve automatically starts to close. The key point here is that the check valve closes completely before any significant reverse flow can occur. This prevents the contents of the discharge line from draining back into the wet well. By doing so, it helps maintain the system prime and prevents overflow in the wet well. There are several benefits to this setup. Backflow prevention keeps the pump and discharge line primed for the next start, which is crucial for quick, efficient operation. It also prevents water hammer, which can cause damage, and protects the impeller from reverse rotation, which could be damaging. Plus, it helps maintain proper levels in the wet well. It's important to remember what check valves do not do. They do not equalize pressure on both sides of the impeller. That's not their role and would actually prevent pumping. They also don't prevent backflow in the suction line. That's the job of foot valves. And they don't regulate flow rate. That's the function of control valves. Their only purpose is to prevent reverse flow in the discharge line. Common types of check valves include swing check valves, ball check valves, and silent check valves. Each has its specific applications and is suited to different flow conditions. In summary, check valves are a simple but vital component that ensures the proper, efficient, and safe operation of centrifugal pump systems by preventing backflow and maintaining system integrity. Let's take a closer look at the relationship between discharge and head in centrifugal pumps. This relationship is inverse, meaning that as the head increases, the discharge decreases, assuming the suction head remains constant. This fundamental concept is captured by the pump performance curve and is essential for understanding how these pumps operate in real-world conditions. Now, every centrifugal pump has what we call a performance curve. This curve shows us how the flow rate, or discharge, relates to the head, or pressure. What you'll notice is that when the system head goes up, the pump delivers less flow. Why does this happen? Well, higher discharge pressure opposes the pump's ability to push liquid forward, requiring more energy to overcome the increased resistance in the system. Plus, the impeller can only impart a fixed amount of energy at a given speed, so it can't continually increase flow when the head rises. Also, at higher heads, internal recirculation within the pump tends to increase, which actually reduces overall efficiency. This relationship has some important practical implications. For example, if you partially close a discharge valve, you're effectively increasing the head, and you'll see the flow decrease. Similarly, if you need to pump liquid to a higher elevation, which increases the static head, the flow will drop accordingly. That's why understanding this inverse relationship is crucial for operators. It helps you control pump output accurately and diagnose performance issues. One key point to remember is that this inverse relationship is unique to centrifugal pumps. Positive displacement pumps, on the other hand, tend to maintain a relatively constant flow regardless of head, making them more suitable for high-pressure applications. Recognizing these differences helps us select the right pump for the right job and optimize system performance effectively. Now, let's look at wear rings and how they help concentrate wear on parts that are replaceable and cost-effective to maintain. Wear rings are installed in the pump to trap wear on a part that can be easily replaced, which protects the more expensive components. This design is quite intelligent because it allows us to save money and time on maintenance. The purpose of wear rings is very precise. They are carefully machined metal rings installed with tight clearances between the impeller and the pump casing. Their role is to create a controlled restriction that reduces internal recirculation, and they accept the wear that naturally occurs from abrasive particles in wastewater. Without these wear rings, abrasive wear would directly damage the impeller and casing. Since these parts are costly and difficult to replace, often requiring a complete disassembly, they need this sacrificial component to take the brunt of the wear. One of the main advantages is economic. Wear rings are inexpensive and easy to replace. When wear causes the clearances to increase, operators can simply swap out the wear rings instead of replacing the entire impeller or casing. This approach significantly cuts down maintenance costs and helps extend the overall life of the pump. Replacing worn wear rings also restores the pump's performance. It reestablishes the original tight clearances, which reduces internal recirculation and improves the pump's volumetric efficiency. Regular replacement is a practical, cost-effective way to keep the pump running at its best. It's important to understand what wear rings do and what they don't do. They do not hold the shaft in place. That's the job of bearings. They do not keep the impeller in position. That's the shaft and keys role. And they are not designed to wear out rings instead of sleeves. That idea is circular and doesn't make sense. Their singular purpose is simply to concentrate wear on a cheap, replaceable part to protect the more expensive internals. This design philosophy exemplifies good engineering economics and practical maintenance planning, focusing on protecting critical parts while minimizing downtime and costs.